Okay, charge coupled device, so CCD. What these are is they're little light sensitive semiconductors. They generate an electric charge when stimulated by light. So it stores this charge in a capacitor. So the charge is proportional to the light intensity and is stored in rows and pixels. So think of it as each row of pixels as a series of buckets on a conveyor belt. So the electronic charge is contained in each pixel or bucket. To discharge the signal, each conveyor belt moves its bucket down the line to measure to the measuring meter. The bucket charge is measured and recorded. Each pixel is read individually and sent to the TV monitor. So that's one way they use this bucket analogy to help you understand how the charge coupled device stores and releases the charge. So the charge couple device is a series of metal oxide semiconductor capacitors, each capacitor representing a pixel made up of 3 polysilicon gates. To digitize the charge from this device, the gates of each pixel are charged in sequence, moving the signal down the row where it is transferred to a capacitor. From the capacitor, the charge is sent as an electronic signal to the TV monitor. So here's your conveyor belt analogy. So moving down and releasing the charge one at a time, row by row. So the CCD to the II, connected by either the fiber optic bundle, which is simply a bundle of very thin optical glass filaments, is durable and simple, but you can't do any spot filming with it. There's the optical lens system, which is a series of optical lenses. So there's a beam splitting mirror, which is moved into the path of the output imaging and diverts some of the light to the desired spot film device, and also allows the fluoroscopist to be able to see what's going on. So viewing systems broken down. So the charge coupled device is a light sensitive semiconducting device, generates an electronic charge when stimulated by light, and stores this charge in a capacitor. Coupling to the image intensifier. So we have here our normal image intensifier, and then this is where we're at here. So there's lenses, and then we have the CCD, we have a spot film device over here. So with the lenses, it diverts the impartial image over to a spot film. So coupling, IIs and television camera tubes are manufactured so the II output window and the window of the television tubes are the same. So 2 methods commonly used to couple together. So there's the fiber optics and the lens coupling. Both of these are out of date, but you need to know the basics of them. So fiber optics, only a few millimeters thick, contain thousands of glass fibers per square millimeter in a cross section. The advantages are they're compact, assembly, easy to move on the II tower, they're rugged, they can withstand relatively rough handling. The disadvantages, they cannot accommodate additional optics required for devices such as cine or spot films. So the lens coupling, it's large in size, you have to be careful when you handle it. So it has objective lenses, so accepts light from the output phosphor and converts it to a parallel beam. When the image is recorded, the beam splitting mirror interrupts, so only a portion of it is transmitted to the television camera. The remainder is reflected to the film camera, allowing visualization of image while being recorded. It's most critical that they are lined properly or you have blurred images, so these lenses have to be lined up, and if you handle the II rough, it can knock these lenses out and they need to be adjusted. So the mirror lens optic system, so the lens system, it conveys the fluoroscopic image from the output phosphor to the II to the video camera, converts into a series of video signals. The signal is transmitted through the cables to the camera or control unit. The signal is amplified and forwarded through another cable to the TV monitor. So the end result is a video signal. Oh, your television monitor. So you can see here, we have the II, we talked about the lenses, spot film, cine camera, or CCD here, and coming up now we're at the television monitor. So the differences from your home TV. There's no audio. It's probably the first thing you noticed, huh? There's no channel changing either, so no remote needed for changing the channels. You can regulate the contrast and the brightness. So the this is the heart of it, is the picture tube. So they also call it a cathode ray tube. This is the final link in the closed circuit television system. So the television monitor, the camera tube or CCD may be coupled to the output phosphor of the image intensifier by either a fiber optic bundle or optic lens system. The fiber optic bundle, like we talked about, is very simple, but yet doesn't allow for spot filming, where the optic lens system allows for spot filming, but it's really sensitive to any kind of rough handling, so there's pros and cons to both. So the viewing system, the television monitor converts the electrical signal into a visible image. So it contains within it a cathode ray tube, which has an electronic gun with grid control, focusing and deflecting coils, an anode, and a phosphorescent screen. So looks kind of the same but different. So you have your electronic gun with your focusing coil and your deflection coil, and you can see here we've got your aluminum reflector with your phosphate and your anode on either side here in your glass envelope. So the electronic gun, it's modulated, which means controlled. Oh, that's by the signal from the camera tube or the CCD. Same pattern as the camera tube or signal from the CCD. Electrons emitted from it are proportional to the signal intensity. The control grid forms the electrons into, into a beam that is controlled by the focusing and deflecting coils and redirected to the phosphorescent screen. The beam sweeps the screen in the same roster pattern as a camera tube. So what's a roster pattern? So the movement of electron beam on the screen of a television picture tube and television camera tube. So the electron beam begins in the upper left-hand corner of the screen and moves to the upper right-hand corner, called a horizontal retrace. Continues till the bottom of the page, then it's called the television field, the whole area. When the beam is turned off, going back up to the left-hand side, we call that blanketed. So next, the top of the screen, it scans vertical retrace, and we call that the vertical retrace when it goes from top to bottom. Finally, is active scanning, where it scans between the two adjacent lines, called interlace. To interlace television fields for a single television frame. So there has to be two interlaced television fields for a single television frame. So this gives you kind of an idea. So it scans right to left, and then you can see the interlace in there. All right, important that you understand the power. So United States power is 60 hertz. So results in 60 television fields per second. So 30 television frames per second. Flicker is not detected by the human eye at rates above approximately 20. So at a frame of 30 per second, each frame is 33 milliseconds long, and we don't have any flicker. So that's just kind of, I'm sure you covered that in your physics class, but I just wanted to bring it up on because we're studying the monitors. So on television monitors, the electrical image coming from the target of the Vidicon tube, and it is canned along 525 lines by a narrow electrical beam 30 times per second. Each scan is called a frame. So only about 480 lines are used per frame because of the time required for retracing. So some special systems have 875 or 1024, so it gives better spatial resolution. It's really important when we get to digital. We'll cover digital next week. So a normal image intensifier has 5 line pairs per millimeter, where a normal monitor has 1 to 2 line pairs per millimeter, and a special one at 1024 has 2 line pairs per millimeter. So as you can see, our image intensifier is got better resolution than what our monitors have. Our monitors are the weakest link. So here's another picture. This is from Bouchon. So when we're looking at other types of monitors, there's the liquid crystal displays, the LCD. These are superior in resolution and brightness compared to television monitors. The heart of the LCD is a liquid crystal layer sandwiched between polarizing layers. When electrical current is applied, the liquid crystals organize and either block light or allow light to pass. And they're thin. There's the LCD, which has a thin film transistor panel, so the TFT, located behind the liquid crystal layer. So the number of TFTs is equal to the number of pixels displayed. TFTs control the current to each pixel and sandwich it on or off by causing the liquid crystals to twist or untwist. The intensity of light is controlled by the current to the crystals, which is controlled by the TFTs, which determines the shades of gray or color. And this gives you a visual display of how LCDs are set up, much different than our monitors. Okay, so plasma monitors. Plasma monitors contain a gas-filled pixel. When the gas within the pixels is ionized, they release ultraviolet radiation. This simulates a phosphor coating in the cell, producing visible light. The current through the pixels is modulated by the electrodes several thousand times per second. Controls the intensity of light produced, make it possible for the plasma monitors to produce billions of shades of color. And then here's their design here. Okay, so what I need you to do is I need you to read the syllabus, and I want you to focus in on Bouchon. Bouchon does a pretty good job in covering this chapter. All right.